Buenos dias, muchachas y muchachos. Welcome, everyone, and hope you are having a wonderful day today. It is another edition of Physics. I'm Mr. Finn, coming to you recorded from neighboring Northville, Michigan. A couple of things today, guys, just getting you up to speed. Had a few questions on makeup homework. Now, I'm not able to put out makeup assignments because I can't get back into the building. It's shut down for the virus. So, if you are missing an assignment, what I would like you to do is send me the whole unit of work. So, if you missed a homework collection for chapter 33, that would be electric fields. You missed a assignment like where I collected 33, number 33 and number 32, two problems, or number 18, number 22, whatever that assignment is. Send me the whole unit of homework and I will give you some makeup points for that. So if you are missing a assignment, now if you're missing points on an assignment, we're just going to work that on. If you got like a 4 out of, half out of 5 or a 9 out of 10 or 8 out of 10, I don't want to see your homework. You guys have already sent that in, so just for people who are missing assignments. So I will try to make contact with those people individually by email, but just wanted to make sure you guys got that as something that you could do to try to put up some of those numbers, make up some work that you missed in the first 8 weeks while we were together. Secondly, Thursday, tomorrow, we are going to have our Google form on statics and fields. Now, if you guys remember statics and fields, electrostatics, remember we had three ways of charging. We had the friction way, we had conduction, we had induction. Those were charging without touching. Charging without touching, induction, involves polarization first, and it may or may not involve grounding. So that was a topic that we discussed for a couple of days. Remember the Van de Graaff generator, a big ball that's able to generate a high amounts of charge. Remember Faraday's law, that a cage could surround an object and there would be no charge on the inside of the cage. So those are all objects. Remember Coulomb's law. That would be force equals K, Q1, Q2 over D squared, the distance between the charges. Remember the definition of voltage as electric potential energy divided by the quantity of charge. So these topics will all be included on Thursday's Google form. All right? So remember, guys, we were supposed to have that test the Tuesday after we came back from St. Patrick's Day. But of course, the school was shut down. So I'm going to be doing that Google form tomorrow. Make sure you guys get a chance to look over your materials and be ready for that. As far as timing goes, I think it's going to be a 3 p.m. availability for that Google form. Try to wrap that up before 6 p.m. tomorrow night. Okay, guys? So hopefully that's okay for you. Today I'm going to look at applied voltage again. We're going to measure it. We're going to evaluate a series circuit, measure applied voltage, and I'm going to introduce you to a new website called PhET.com. It's a pretty simple website by the University of Colorado. You can log on, you can create your own circuits. You simply just click and drag the items into the area that you want, connect them with wire, and you can make a circuit run. It's an easy way to do a lab, guys, and you can get any kind of resistors or capacitors that you want, but we're going to focus mainly on resistors and voltages for the time being. So check that out, PhET.com. Make sure you guys can get a little lab experience, and I'll have an assignment coming up at the beginning of next week for that. Okay? But for the meantime, let's take a look at measuring applied voltage, or at least evaluating a series circuit with the rules that we saw yesterday, and how we're going to measure applied voltage or voltage drop. Okay, guys, we're here at the magic board here, checking out a little example on a series circuit. And you can see I have a 6-volt supply. So that would be 4 D-cell batteries if you're wanting to make this at home. I got a wire going from there, the front of the battery, to a 1 ohm resistor called bulb 1. I've got another wire going from the back of that bulb to the front of bulb 2. I'm going to show you this in the lab setup in just a minute. From the front of bulb 2, the back of bulb 2 rather, back to the back of the battery. Now I know I've got one complete loop. There's only one way for the current to travel. So I'll draw a dotted line, and the dotted line will show me current. Current running through the circuit. And you can see there's only one path. So this defines a series circuit for us. Now, a couple of things that we knew from yesterday, the series rules. Number one, we had to identify it as a series circuit, which we did. We had to add resistors together for total resistance. So total resistance is the sum of the two resistors. 2 ohms plus 1 ohm to give me 3 ohms. So that's my total resistance. It's as if I could take these two resistors out and replace them with one resistor that did exactly the same thing. I'll show that in the next frame. For my total current, I've got 6 volts divided by 3 ohms because it's voltage divided by resistance to give you current. Well, that will give me 2 amps. So that means that there's 2 amps flowing through the circuit. Now, one of the questions I like to ask guys is, hey, where is it 2 amps? Remember the points we had in the circuit yesterday, A, B, C, D, E? Well, the answer is everywhere. Everywhere, Mr. Finn, because there's only one flow rate. That's kind of a trick question. I don't know why people ask that, but it gets asked a lot. So, 2 amps through the circuit, 3 ohms in the circuit. Now, what I'm going to do is draw a resistor reduction diagram that we're going to use a lot when we get to combination circuits, so I need you guys to be kind of familiar with how it goes. Okay, guys, what did Mr. Finn do about resistor reduction? What do you mean by that? Well, we're going to take these 2 resistors and combine them and redraw the circuit so that there's only one equivalent resistor. That's called resistor reduction. I've drawn that in blue up here. I took the 2 and the 1 ohm out and I put a 3 in its place. Well, that wouldn't change the current because 6 volts divided by 3 ohms still gives me 2 amps. So it's as if I replace the 2 resistors with one equivalent resistor. That's why sometimes you'll see R total given as R/EQ or R sub EQ, because if you took the 2 out, then that one equivalent resistor would be the same as R total. Are you guys okay with that? We're going to come back to that next week. But if I measure the voltage, the applied voltage of just that resistor, well, in this diagram, the voltage across the 3 ohm equivalent is simply 2 amps times 3 ohms to give you 6 volts, same as the total. But over here, when I go back to my original diagram, carry current back with me, I'm going to figure out what VR1 is. 2 amps times 2 ohms, or 2 volts. And for the V sub R2, the voltage across R2, that's 2 amps times 2 ohms, or 4 volts. Notice, guys, that 2 volts and 4 volts together is 6 volts. So, we've done a quick evaluation of our series circuit. Now, where do we measure these things? If I had an ammeter, a voltmeter, a multimeter rather, set to measure current, I would put that in series with the rest of my circuit. So an ammeter must be in series. So if you guys are going to put together this circuit on the FET simulation, you want to put your ammeter in the line with the resistors. But what about a voltmeter? If I want to measure voltage, how does that go? Well, a voltmeter, my friends, must be outside the loop. So if I want to put a voltmeter here, I've got to attach it just like I attached it yesterday on the video to the bulb on either side of the bulb, but that attachment has to be outside of the loop that you are already making. It's called a parallel setup. The voltmeter must be hooked up in a separate loop called a parallel loop. And I'll show you that in just a few minutes here on the lab. Okay? Everybody okay? All right, let's look at the lab now. Okay, guys, here I am with the setup. I've got my white wire coming from the back of the battery to the bulb, front of the bulb, a yellow wire from the back of bulb 1 to the front of bulb 2, and a red wire from the back of bulb 2 all the way back to the supply. And you'll notice that this wall bulb is lit, while this one is not. But we know there's current going through there because it's a series circuit. If I disconnected the circuit, nothing would be lit. So therefore, the fact that one bulb is lit and one bulb isn't doesn't mean there's not current going through it. We just might not have enough current to light the bulb. So I'm going to take my voltmeter here, and I'm going to hook this up, maybe so you guys can see it. And I'm going to touch on either side of the bulb. So I'm going to do bulb 1 first. You guys see I got about 2.6 volts. That's almost all the voltage of the batteries. The batteries only have 3 volts. This one, about 0.7 millivolts. So really, looks like I'm getting a reading. Yeah, about point, settles in about 0.7. So that's, or 70 millivolts. That means that I've got very little voltage across this bulb and a lot more, or most of the voltage across this bulb. So it's a little bit different than the example that we did, but I'm hoping you guys can see how we attached to measure voltage by working across the bulbs and outside of the main loop. We don't have to disconnect any wires to hook up our voltmeter. We would have to disconnect wires if we were hooking up this multimeter to measure current. We'd have to take one of these lines out, stick it to the back of the ammeter, and put the ammeter right in here. I'll show you how we do that. So what I'm going to do is I'm just going to turn it on to the milliamp setting. And I'm going to disconnect this and hook it to the first lead of my ammeter. And then my other, I'm just going to touch to the battery. And you can see my light bulb lights up. And I'm looking at about 66 milliamps. Hopefully you can see that. About 66 milliamps. 65.9 actually. So I made a change to measure current. Now I actually had to change the input too, because my input has to be where it says milliamps and not volts. So if I wanted to be on the volt setting, I'd have to be there, and I have to dial my object to volts. If I wanted to measure current, milliamps, I would have to be on the right input. When you guys work for FET, it won't be that way, but that's what we do in the lab. Okay guys, well that's just about it for today. We evaluated a series circuit to measure voltage, applied voltage. Remember those two voltages were different for the types of bulbs we had. The voltage measurement must be outside the normal loop, otherwise called a parallel hookup. If we're measuring current, that ammeter or multimeter set to measure amps must be in the original loop. Okay, we'll do more with that, but I would like you guys to check out the FET simulation website so we can get a lab going next week. Tomorrow, I'll do a little bit of review on statics in fields, but I'm going to introduce you to the basic parallel setup. Guys, if you're thinking that series is easy, I'm hoping that's great, because when we get to combination circuits, it's not as easy as just a straight series or a straight parallel. But have a great day, guys, and make sure you keep up with the homework. If there's any questions about the homework questions, please email them into me, or we can get them on the Google Meet today. And again, apologize for second hour's Google Meet. I had technical difficulties yesterday, but hopefully you're good to go from, the day before. But hopefully you're good to go on yesterday's Google Meet at noon. So we'll try to get back on the regular schedule for the next time the following week. Have a great day, guys, and we'll see you tomorrow.